Today we're going to have a presentation on understanding the Canadian Electrical Workspace Safety Standards. The presentation will be given by Simon Giard-Leroux, who has a particular expertise in the analysis of electrical networks. As a member of the Power System Studies and Commissioning team within the Energy Group at the engineering firm CSA in Sherbrooke, Quebec, Canada. He has produced more than 100 studies for clients throughout Canada and the USA. Short circuit, protection coordination, arc flash, transient recovery voltage, cable ampacity, etc. He also has a vast experience in the commissioning and testing of power equipment in factories and substations. Mr. Giard-Leroux obtained a bachelor's degree in electrical engineering from the University of Sherbrooke and holds a specialty in power systems from the Institute of Electrical Power Engineering in Montreal. And I wanted to thank Simon for taking the time to present with us today. And I'll turn the screen over to him.
Okay, thank you, Ted. So I would like to begin by thanking EasyPower for inviting me to host this webinar. So let's start here. So the title of the webinar today is Understanding Canadian Electrical Workplace Safety Standards. So we'll have a detailed look at the CSA Z462 and the CAN ULC S801 standards. So as Ted mentioned, I'm Simon Giard-Leroux. I'm a professional electrical engineer at CSA, and I work in Sherbrooke, Quebec. So the plan for the webinar today, we'll start by stating the webinar objectives. Then we'll go over an introduction of the shock and arc flash hazards. So there's two types of hazards when dealing with electricity. So there's shock and arc flash. So I'll do a summary of these risks. Then I'll do an overview of the electrical safety standards that apply in Canada. Then I'll go in detail about the CSA Z462. Then afterwards, I'll go in detail about the CAN ULC S801. Then I'll end the webinar with some conclusions and recommendations, and then we'll have a question session. So the webinar objectives for today. So by the end of this webinar, you should be able to differentiate the risk between arc flash risks and shock risks. So there's a difference between the two, so I'll go over the difference and you'll be able to distinguish between both. Then you'll be able to define the risks associated with arc flash. Then you'll be able to read arc flash labels. You'll also be able to define the PPE, so the personal protective equipment that you're gonna need to wear when performing live work. You're gonna know how to safely perform live work and how and when to use the CSA and the CAN ULC standards. So this webinar today counts as an electrical safety training. So this type of training is defined in the CSA Z462 standard in section 4.1.7. So basically today we're going to cover the content of a typical electrical safety training. However, it's not compliant with the 4.1.7.1.5 clause that says that it shall be in a classroom or on the job. So since this is online, this is not compliant with that clause. So an introduction on shock and arc flash risks. So it's important first to understand the difference between a shock and an arc flash. So what is a shock? So an electrical shock is the reaction or injury caused by the electrical current passing through the body. So when the shock is fatal, when the person dies, it's called an electrocution. So the difference between a shock and an electrocution is if the person survives or dies. So for example, a taser gun, it's designed to be to induce a shock and not electrocution if used properly. So what can happen after an electrical shock? So the heart can start to fibrillate. So heart fibrillation can occur. So in the next slide, I'll explain to you what the heart fibrillation is. There can be involuntary muscle contraction. So the respiratory muscles can become contracted and block the the ventilation of the human body. You can have severe burns. There's also a possibility of trauma associated with electrical shock. So, for example, being shocked and falling from a bucket truck, for example. And you can also develop rhabdomyolysis. So rhabdomyolysis is when you have an electric shock and you can die a few hours later. It's very important when you have an electric shock to go to the hospital to get checked to make sure that you don't end up developing a rhabdomyolysis that can cause death. So what is heart fibrillation? So this happens when the shock is going through the heart. So there's a certain period in the ECG of the heartbeat where it's vulnerable, that the heart can start to beat uncontrollably, and this can lead to death by heart fibrillation. So basically the chance that this occurs is about 1 in 200 occasions. So the IEEE standard 80 defines the human body impedance. So the body internal impedance is around 300 ohms, and the skin impedance can vary from 500 to 3000 ohms. So a typical impedance from hand to hand would be 1000 ohms, and hand to feet would be 1000 ohms also. So let's say you want to calculate the current that goes through a person's body. You can use Ohm's law. So this is for a single phase system only. So for example, for a domestic outlet at 120 volts in Canada, you simply divide the voltage by the internal resistance of the body, and you get the current. So it's safe to say that impedance does play a major role in limiting the current that goes through a person's body. So here you can see a figure that says the range of shock ampacity. So it starts at 1 milliamp, which is the threshold of sensation. Then at 10 milliamp, you start to that you can't let go, so your muscles start to contract. At 100 milliamps, your heart stops beating. At 300, your breathing stops, and you can develop severe burns at around 900 milliamps. So the effect of the current on the human body is very dependent on the following elements. So you have intensity, which is the ampacity in amps. You have the duration of the shock. You have the person type, so the person's height, weight, skin thickness can affect the body impedance. There's also the current path inside the body. If the shock goes through the heart or does not, changes the danger of the shock. And there's also current frequency. So there's the frequency of the AC or the DC that can affect the effect of the current on the body. So according to the Guinness Book of World Records, the first place for the largest shock that was survived by someone was a 340 kilovolts AC shock that happened in Utah, and the worker survived. And the second place was on a 230 kV line in LA. So some reminders. So what to do in case of an electrical shock if the victim is or might still be in contact with the current source. You need to make sure you do not touch the person. If the person is still in contact and you touch it, you might end up being shocked as well. So the first step is to de-energize the system at the source, then go help the victim, or try to eliminate the contact between the victim and the source by using an insulated pole or object. So make sure the pole is insulated and is not conductive. Otherwise, you could get shocked as well. So you need to use the insulated pole to free the victim without touching the source. Then once the victim is away from the source, you need to immediately call emergency and or an ambulance. And it's also very important, if you witness someone getting a shock, you should accompany the victim at the emergency, because the victim might lose consciousness afterwards, and you need to make sure that you're there to state to the doctor and the nurses what were the situations of the shock. So once the victim is not in contact with the source anymore, you need to call emergency and or an ambulance. So if the victim has lost consciousness, has no pulse, or is not breathing, you need to perform CPR until first aid arrives. So it's important, if you know CPR, to perform it, because the heart can stop beating, but it might not be damaged. So if you perform CPR enough, the person might be saved in the end. So these were the details of a shock. Now let's talk about arc flash. So what is an electric arc? So it's defined as a visible electrical current in an insulating medium such as air. So other examples of insulating mediums are oil, for example. So it's the arcs are created by the ionization of the insulation, which occurs when the potential difference becomes greater than the insulation capacity. So when this happens, it's called an insulation breakdown, and you see the current going through the path of least resistance. So important notes about arc flash. So arc flash damages are due to the explosion of the arc itself. So arc flash happens when there's a short circuit inside a live electrical equipment, and then there's a blast which projects energy towards the worker. So the main danger for arc flash is severe burns and amputation. So arc flash can cause death, can cause major injuries and burns, and also can cause major monetary costs of an arc flash incident. And it's often in the $1 million range when you include medical costs, production losses, equipment. I'm sorry, I'm getting told that there's a problem with my display. Is that correct? Okay, well, I'll keep going then.
I actually, for some reason, I'm getting a little teeny bit on the very right side of your screen. I can see it.
Is it blocked?
Well, it just went.
Is that there?
Actually, yeah. It just,
okay, great, perfect.
I could see 95% of it. There was a little something blocking the right side.
Okay, great. All right, so I'm glad it's fixed now.
Okay.
All right, so there's a danger of for arc flash, but also monetary costs when an arc flash incident happens. It can go in the $1 million range. So you can take into consideration the medical costs, production losses, the equipment replacement, and the insurance. The costs can go up quite considerably. So the arc flash formulas are found in the IEEE 1584. So these formulas apply up to a voltage of 15 kV. But if you want to calculate arc flash above 15 kV, then you can use the Lee method, or you can use software such as ArcPro. So rule of thumb, so basically the arc flash formulas are very, very complicated, especially the IEEE 1584 2018 version. But the rule of thumb for arc flash energy calculations is that the energy equals the current squared times the time of exposition. So remind yourself that the two main aspects that affect the energy is the current, the fault current available, and the time of the exposition. So when an arc flash occurs, it can go up to 4 times the sun's surface temperature. So at that temperature, the clothes can be easily ignited, and that can cause severe burns, which can be fatal. And during an arc flash event, the metal will vaporize. So the metal will not necessarily melt. It will vaporize and become a gas, and will experience rapid expansion. So this effect can create shock waves that can rupture eardrums, collapse lungs, and even cause death. And there are also metallic sections that can be vaporized and blasted, which can harm nearby workers and or ignite their clothes. So apart from a bad maneuver, bad maneuver can cause an arc flash. There are different causes of an arc flash. So there can be dirt, corrosion, condensed water, animals that can cause a short circuit inside a panel, for example. There can be a flashover on 2 phases. So for example, if there's an insulating medium that there's an over voltage on 2 phases, then there can be a flashover, and there can be a a face-to-face short circuit. And for example, poor working procedures and poor engineering can increase the risk of an arc flash. So when we deal with arc flash, we speak in calories per centimeter squared. So this represents the incident energy of an arc flash. So 1.2 cals, which is one of the thresholds, this corresponds to putting a lighter under a finger for 1 second. Then 12 cals, it's the equivalent of putting your hand on an oven element for 6 seconds. So this starts to be a lot of energy concentrated in the same spot. And what happens to clothes when an arc flash is over 8 calories? So at 10 cals, cotton clothing will be set on fire, and at 18 cals, untreated clothing will be set on fire. So at 40 cals, there's enough energy to make 1 liter of ice boil. So not 1 liter of water, but 1 liter of ice. So it goes from 0 Celsius to 100 Celsius in 5 seconds. So that's a lot of energy. And when the energy is over 40 cals, then the temperatures can go over 3000 Celsius and can be reached and applied to human skin. And this is the only way to execute the terminator. So other effects of an arc flash, there's the noise effects. So for those of you who do housework, for example, a domestic vacuum will be 80 decibels, but an arc flash can produce a noise level up to 140 decibels. So let's say a jackhammer, this is about 130 decibels, and the jet motor is around 140 decibels. So it's about the same sound as a jet motor. And there's also the shrapnel, so the bits of scrap metal and equipment that can go towards the worker. So here are some statistics about arc flash events. So based on an IEEE white paper, so in cases of arc flash, over 50% of all arc flash are under 1.2 cals, but then 34% are between 1.2 and 8. Then you have 11% that are between 8 and 40, and then 4% that are over 40. So this was the overview of the safety. Now we'll go over the electrical safety standards that apply in Canada. So the applicable standards, you have the Occupational Health and Safety Act, you have the Canadian Electrical Code, specifically Rule 2306 and Appendix B. You have the Canadian Bill C45 that I'll go in detail over in the next slides. You have the CSA Z462, which is based on the NFPA 70E. So this one will be covered in the presentation. Then you have the IEEE 1584 standard, which defines the formulas used for calculating the arc flash energy. Then you have the CAN ULC S801 standard, which is the safety standard for utility workers. So a bit of an history about arc flash. So the first history starts in the year 1979. So that's the year of the first version of the NFPA 70E. So the NFPA stands for National Fire Protection Agency in the United States. Then in 1980, there's Lee, who was a researcher that first got interested in arcs. And then in 1995, there was arcs and limits of approach that were established. And specifically in Canada, the first version of the CSA Z462 was out in 2008. Then there were 2 more versions in 2012 and 2015, and now the latest version was out in 2018. So here's an example of the Bill C45. So Bill C45 states that if electrical error happens and the safety of a person is jeopardized, for example, if there's an arc flash on one of the workers, the company can be held responsible and can be fined for this. So for example, here in 2009, Domtar was fined for $87,000 after a worker was injured since he was exposed to an arc flash without wearing his PPE. And then there was an investigation that proved that the company did not have due diligence and did not correctly train his workers. So they were fined as well. So the Occupational Health and Safety Act states that every employer shall ensure to take every reasonable precaution to ensure the workplace is safe. And the employer also needs to train employees about any potential hazards. And the employer needs to supply a PPE, so personal protective equipment, and ensure they know how to use them. And there's also obligations for the workers. So they shall work in compliance with the OH&S acts and regulations. They shall use the PPE and clothing as directed by the employer. And they shall take reasonable care to protect the health and safety of the worker and of other workers present while the worker is working. So the worker shall make sure his safety is ensured and the safety of others around him too. So the applicable codes, so in the Canadian Electrical Code, Rule 2306, it states that all electrical equipment that are susceptible to being worked on while energized shall be field marked to warn persons of potential electric shock and arc flash hazards. And then in Appendix B, the code states that CSA Z462 can be used to evaluate arc flash hazards, and also states the IEEE 1584 can be used to calculate the arc flash energy. So just one slide on the IEEE 1584 2018. So this is the latest update of the algorithm used to calculate the arc flash energy. So in the CSA Z462 Appendix D, right now it's the ancient version of the IEEE 1584. Right now in Appendix D, you can find the 2002 version only. So in the next version of the CSA Z462, the appendix will be updated to the IEEE 1584 2018. So this 2018 version is the first update since 2002, and this new version of the standard is very much more complex than the 2002 version. So now there's electrode configurations, and there's now enclosure size of the equipment that enter in the calculations. So now we are at the CSA Z462 section. So the name of the standard is Workplace Electrical Safety. So a summary, so CSA stands for Canadian Standards Association. So the CSA Z462 standard defines the requirements and provides guidance for persons exposed to shock and arc flash hazards when working with live electrical equipment. So it defines safety management systems, safe work procedures, how to select PPE and safety devices, how to identify qualified workers, so how to know if someone is qualified, how to train qualified workers, and also what's the hazardous work that can be performed by qualified workers. So the history of the standard, well, it was developed in parallel with the NFPA 70E and harmonized as much as possible with this American standard. So as mentioned previously, this is the fourth version. The 2018 version is the fourth. So let's go in some definitions in the standard. So what is a qualified person as per CSA Z462? Well, if we refer to section 4.1.7.1.2, a qualified person is trained in and knowledgeable about the construction and operation of the equipment or work method. He is trained to identify and avoid electrical hazards. He's familiar with the proper use of the equipment and procedures, and also to enter the limited approach. So the limited approach, I will explain to you later what that is. So to enter it, the worker should be trained to first distinguish live circuit parts. Second, determine the nominal voltage. Third, know the approach distances. Fourth, decision-making process to conduct electrically safety work. And last, how to select appropriate test equipment. So it's responsibility of the employer to determine through supervision and inspection that each worker is complying with the safety-related work practices. Now, what are the host and contract employers' responsibility? So this is defined in section 4.1.8. So the host employer shall inform contract employers of first known hazards related to the contract employer's work, and then information about the employer's installation. And then the employer's responsibility is defined in section 4.1.3.1. So the employer's responsibility are to establish lockout procedures for the organization, provide training to workers, provide equipment necessary to execute the procedure, and also to audit execution of the procedure at least annually. And then another definition. So the standard states that to establish an electrically safe work condition in section 4.2 states that you need to determine all possible sources of electrical supply, because sometimes there can be multiple supplies through a certain device. You need then to interrupt the load current. You need to open the disconnecting devices for each source and visually verify the devices are fully open. Then you need to apply lockout devices. Then you need to verify that each phase is de-energized using a test equipment. And then finally, you need to apply properly rated ground connecting devices. Then the standard states when energized work may be performed in section 4.3.2.2. It's safe to say that energized work should be avoided when possible, but it may be performed when de-energizing introduces additional hazards, when the task is unfeasible in de-energized state because of equipment design or operational limits, or when the voltage is less or equal than 30 volts. Then another interesting section of the standard is the arc flash study review update frequency. So this is stated in section 4.3.5.6.2. So it says that the arc flash study shall be updated when major changes occur, or at an interval not to exceed 5 years. So it's either 5 years or a major change. So for arc flash labels, there are two ways to go about creating them. So the first way is the incident energy analysis method, and the second way is the arc flash PPE category method. So the incident energy analysis method, you need to do a survey of the electrical installation. You need to model the network in a software like EasyPower, for example, and then you run calculations. Then you get arc flash incident energy results in calories per centimeter squared. So when you use this method, the label must only show the calories and must not show the category of PPE. So if you want to show the category, you need to use the tables 6A or 6B, and you cannot show the incident energy and the category on the same label. It has to be one of the two, but not both. So this is prohibited in the standard. So it's safe to say that this table does not apply when you use the incident energy method. It only applies when you use the arc flash tables method. So the categories that exist, you have categories 0, 1, 2, 3, and 4. So 0 stands for an energy between 0 and 1.2 cals. 1 stands for energy between 1.2 and 4. 2 for an energy between 4 and 8. 3 for between 8 and 25, and then 4 for an energy between 25 and 40. So when you use the incident energy method, you need to use table 3 to determine what PPE you're going to wear. So this table defines the PPE to wear between 1.2 and 12 cals, and then for energies over 12 cals. So in this table, there are some items that are optional. There's a N in parentheses at the end, so this means optional, and then SR means means it's obligated. So what does 1.2 cal kit resemble? Well, this is a worker that's currently dressed in a way that can protect him up to 1.2 cals. So he has a hard hat, he has hearing protection, so ear plugs, he has safety glasses, untreated fiber clothing, long sleeves, untreated fiber pants, and leather insulated work shoes or work boots. Then between 1.2 and 12 cals, you can buy a kit that contains a coverall, which is rated for 12 cals. Then you need rubber insulated gloves. You need leather gloves above them. You need a balaclava that covers the neck and the face except the eyes. And then you need a helmet with a face shield on. So all the equipment has to be rated for 12 cals. Then this is a kit that's designed for use between 12 and 40 cals. So as you can see, the suit is pretty large and encumbrant. So with the large hood, it can be hard to see, and it can be hard to do precise maneuvers in the switch gears. So this can be worn only when doing imprecise things, because it can be hard to properly see with this hood. And there are other kits with higher rated energy that exist on the market. So here's an example of a 100 calories per centimeter squared kit. But when you're over 40 cals, we recommend not to work on live equipment, because these kits first will be very expensive and then will reduce the mobility of the workers, and it will be hard to see, so it might increase the risk of causing an arc flash in the gear. So they exist, but it's not really recommended to work on live equipment above 40 cals. So what about jewelry and other conductive items? Well, for example, wedding bands, metallic torches, or metallic watches. So these items are prohibited within the restricted and arc flash boundaries. So it's very important to pay special attention to underwear. It needs to be in natural fiber only. It's very important to check for prints on shirts, because prints on shirts can melt and injure the worker even more. So avoid prints on shirts. PPE maintenance. If there's oil or flammable product on arc flash rated PPE, you need to make sure to wash it off or replace the PPE, because this can lower the fire protection of the equipment. Also check regularly for cuts or broken stitches, because cuts or broken stitches can reduce the protection of the worker. And then you need to make sure you never use fabric softener on fire resistance clothing, because this can completely remove the fire resistance from the equipment. So make sure you never use fabric softener on these PPE. And also for objects and tools, make sure you only use the minimum tools required for the job to reduce the risks. Beware of what's in your pockets so it doesn't fall off or anything, and you need to inspect your tools conditions. Also, always use appropriate work equipment. Use insulated tools whenever possible. So this is the table used when you use the arc flash PPE method. So these are pre-calculated arc flash results, but these don't cover every result. So if your installation is not covered in this table, then you need to do the incident energy method. So this, for example, says that for this type of equipment, this type of fault current, this clearing time, the arc flash category is 1. You also have here several other cases in table 6A, and then you have 2 others here at the end of the table. And then 6A was for AC systems, but you also have table 6B, which is for DC systems. So this table is is shorter than the AC, but you can use it to do arc flash assessment with this table if your equipment is within this table's application. So it's important to avoid live work when there's evidence of impending failure. So the standard in section 4.3.2.2.4 defines impending failure as there is evidence such as arcing, overheating, loose or bound equipment parts, visible damage or deterioration. So a way to make sure that there's no evidence of impending failure, you need to visually inspect the equipment. You need to verify for signs of previous burns or overheating. So for example, doing thermal imaging. You need to verify for signs of water or humidity inside the equipment. And also another method is to gently approach your hand towards the equipment to verify any current overheating with gloves, of course. So the CSA Z462 defines 3 boundaries with regards to shock and arc flash protections. So the first boundary is called the arc flash boundary. So it's defined as the distance at which you need to go back from the source of the arc for the energy to drop at 1.2 calories. So for example, if you have arc flash label that says 8 calories at 18 inches, then you need to go back, for example, at 2 or 3 meters for it to drop at 1.2 cals. Then limited approach boundary. This is for shock protection only. So basically, it's the radius around the live conductors where there's a risk of shock, and you need to be qualified to enter the limited approach boundary. And then the restricted approach boundary is a boundary when there's an increased risk of electric shock. So you need to be qualified and wear a shock protection PPE in that case. So the limited approach boundary and restricted approach boundary, they can be found in table 1A for AC systems in the CSA Z462 standards. So you have, for example, on the first column, you have the voltage range, then you have the limited approach boundary, and then you have the restricted approach boundaries. So these are fixed for each voltage level. So what is the working distance? Well, working distance is the distance between the live bus bars and the chest of the worker at a distance which is typical to work in this type of installation. So there are 3 typical working distances. So for low voltage MCCs and panel boards, it's 18 inches. For low voltage switch gears, it's 24 inches, and for high voltage or medium voltage switch gears, it's 36 inches. But there can be more than these 3. For example, if you're working in a bucket truck, then the working distance is increased. So this is figure C1 of the standard. So this defines the limits of approach. So the dot at the middle of the sphere represents the point of the source of the arc flash, so the live bus bars. Then you increase the radius, and then you reach the restricted approach boundary, the limited approach boundary, and then the arc flash boundary, the more you go away from the source of the arc flash. So this is a 3D image we've made to show what is represented by the working distance and the arc flash boundary. So you can see, for example, this is a one cell of switchgear that's open. Well, the working distance is the red circle, and then the yellow circle is the arc flash boundary. So remind yourself, what's on the label is the incident energy at the working distance, and then the arc flash boundary is the distance at which you need to go back for the energy to drop to 1.2 cals. So again, this is another way to represent the boundaries in arc flash and shock protection. So you have the limited approach boundary for shock, then you go closer to the panel, then it's restricted approach, and the flash protection boundary is way out the limited approach boundary to the left, and then you have the enclosure and the live bus bars, which are in the middle of the enclosure. So the CSA Z462 gives some recommendations about the arc flash labels that need to be put on equipment. So the bare minimum label is the first one. So it states only warning and arc flash and shock hazard. And then you can go a step further and add the incident energy at the working distance. So you see it stated in cals per centimeter squared. There's no category there because the incident energy method was used. Then there's the arc flash boundary, so the distance at which you need to go back for the energy to drop at 1.2. Then you have the nominal system voltage, which is the line-to-line system voltage for this three-phase system example. Then you have the date of the arc flash analysis. So when the date exceeds 5 years, then you know the arc flash study needs to be redone or updated. Then you can go another step further and include reference to the CSA Z462 standard. You can include limited approach boundary for shock protection. You can include restricted approach boundary. You can include glove class. You can also include the equipment name. You can include the company that did the study. You can include the date of the analysis, and you can also refer to the method used. So in this case, the method used was standard IEEE 1584. So you can go even a step further than that. So this is an example of CIMA Plus labels. So we put danger, arc flash, and shock hazard, all the distances in centimeters and inches, meters, or feet. And then we list the PPE in the label. So you never have to go back to the standard to say, oh, which PPE are required. We put it directly on the label. So this is it for the CSA Z462 standard. Now we're ready to jump in the CAN ULC S801 standard. So this standard name is Standard on Electric Utility Workplace Electrical Safety for Generation, Transmission, and Distribution. So ULC stands for Underwriters Laboratories of Canada. So this standards defines electrical safety requirements for utilities or high voltage work. So this applies more to linesmen, for example. So for example, as you saw in the CSA standard, this was more for industrial or medium, like 208 to 15 kV arc flash risks and dangers. But this ULC standard is more applied for high voltage applications. So the first edition was published in 2010 of the S801, and then the second and latest edition was published in 2014. So as you can see here, it's an excerpt from the standard. So the standard applies to voltage levels up to 800 kV AC and 600 kV DC. So section 4.1 defines the roles and responsibility of the employers. So how and when to provide safety training, how to handle visitors. And then it also states the roles and responsibilities of the workers. So what are the rules? What are the safe work practices, the tools, how to report unsafe practices, etc. So it says, for example, every employer shall ensure the safety and health at work of all its workers, and only qualified workers shall perform work on the power system. So you see, it's very similar to the CSA Z462, but more oriented towards linesmen and utilities. So section 4.2 defines the qualifications of a worker. So how to say that a worker is qualified? Well, he has to be trained in the skills necessary to safely and proficiently carry out all tasks assigned, and also demonstrate competence in carrying out such tasks. Then you have section 4.3 that defines that all electrical equipment need to be easily identified and located to make sure that when live work is done on utility systems, that work is done on the proper equipment, on the good equipment, not another one that was badly identified. So it's very important to have up-to-date plans and to safely identify, clearly identify all equipment on the utility network. Then section 4.4 defines the work planning requirements. So how to do work plans. So safety planning, for example, it says you need to start with a site visit to identify and document high-risk hazards and critical issues. Then all workers need to be informed of the hazards that affect them. Then methods on how to identify hazards, eliminate them, assess and control risks. Then it recommends some record-keeping methods, and then it specifies emergency response plan requirements. Then section 4.5 defines how to select PPE. So PPE for general PPE, head, eye and face, hearing, skin, body, foot, hand, and fall. So mostly this section doesn't go into much detail, but only refers to external standards. For example, it refers to CAN CSA standards or ASTM standards to define the PPE. Then section 4.6 defines how to build an emergency response and first aid plan. So it states that a plan must exist for emergency response, that a plan must contain risks, emergencies, procedures, communication methods, location of emergency facilities, etc. It states also the training requirements for emergency response and first aid, and also some tips for fire protection. Then you get to section 5, which defines the approach distances. So the minimum approach distances for lines and utilities shall be established by the utility and approved by a professional engineer. So as stated here in 5.1.1.1, it states that the distances shall be established by the utility and approved by a PNG. Then you get into section 6 that defines how to select and how to use protective tools, equipments, and devices. So, for example, it covers insulated versus conductive equipment, when to use insulated versus conductive, what types of protective covers to use, how to use and what to use for temporary grounds and bonds. Then GFCI, so ground fault current interrupters, and then how to select voltage detectors and voltmeters. So these ULC standards does not really contain much tables or much figures, so it's mainly more references to other standards. Then section 7 defines live work. So it says the training requirements before performing live work, how to use insulating materials and work procedures, how to locate and identify the equipment, how to categorize the line work, deal with ground and line potential, how to work on metering units, how to work on battery banks, UPSs, and chargers, and also how to work on underground versus aerial line systems. Then you get to section 8 that defines the requirements for arc flash protection. So it says how and when to perform risk assessments, how to control arc flash risks, what to wear as arc flash PPE, and how to care for arc flash PPE. So we talked about it a little bit during the CSA portion, so the same guidelines apply. So for example, here you see when live work is performed above 200 volt AC, then you need an arc flash risk assessment. Then you have section 9. So sometimes linesmen need to work near communication antennas or radio towers. So this section says the limits of exposure to RF radiation in Canada with regards to Health Canada safety codes. Then you have section 10 that defines how to isolate electrical equipment. So when you need to work on a specific section of an equipment but not live, you need to isolate it. So this states the methods of work that needs to be used to isolate the equipment. So how to ground and block the systems with lockout and tagging procedures. And then section 11 defines how to work safely near electric utility systems. So this applies not necessarily to utility workers, but also non-utility workers. So how to deal with the safety of these persons. How also to do a vegetation management plan on your distribution or transmission system. And how to work safely around generation systems and rotating machines. So we're now getting to the conclusion and recommendation section. So it's important to state some advices. So you need PPE management process. You need work procedures that are clearly defined and that your workers know. You need to clearly manage your limits of approach, so every worker is up to date and has the proper limits of approach. You need to update your single line diagrams. You need to plan for spare fuses of the same size and types than the other ones in place. And you need to review and revise your arc flash study by a PNG either for every major modification or every 5 years. Then here are some tips that you can use to mitigate arc flash events. You can change the settings of your protection devices. For example, here in the bottom left, it's an example of the settings for a breaker. So you can adjust the breaker settings with protection coordination study to make sure that you maintain proper coordination. You can add more protection to reduce the arc flash energy. You can replace protections with quicker ones. You can also modify your work procedures. So as for additional protection, so examples, you can use arc flash detection relays. So for these relays, you have a fiber optic sensor in your switchgear, for example, and when it senses the light of an arc flash, it will trip the main breakers. So for example, this is one of the additional protection that can be used. You can also use arc-proof switchgears that are made to dissipate the energy of an arc. You can use maintenance mode protection settings on your relays. So for example, when you work live, you make your main breaker quicker, so the time of exposure is lowered, and then this can lower the incident energy. You either can activate it with a switch or with a motion sensor, and you can also buy automated rack-in or rack-out breaker systems. So this is a picture of an example of an arc-proof switchgear. So you see there's a chamber that allows the arc to exit the switchgear, so this lowers the energy that the worker is exposed to. And also some working procedure modification tips. You have possibility of racking and deracking from a distance location. You have the possibility to use insulated tools. And also you need to proceed with a maintenance schedule based on the manufacturer's recommendation. So to finish this webinar, so I hope this webinar allowed you to differentiate between arc flash risks and shock risks, define the risk associated with arc flash, how to read arc flash labels, how to define the PPE to wear when performing live work, how to safely perform live work, how and when to use the CSA Z462 versus the CAN ULC S801. And also remind yourself that it's better to avoid live work whenever possible. And finally, an arc flash study allows workers to know the potential risk associated with live work and secure the workplace to qualified workers only. And remind yourself that electricity will always be a source of potential danger. So thank you very much for your time. Now is the question period. So please submit your questions through the question box. So I can see the first question is from Prem Devkoto. So his question is arc flash calculated as per working distance? How are these working distances defined? So basically, yes, the arc flash energy on a label is always given at the working distance. So for the working distance, there's 3 typical working distances that are defined in the CSA standard and the IEEE 1584. So you have 18 inches for low voltage panel boards and MCCs. You have 24 inches for low voltage switch gears. So for example, 600 volt switch gears. And then you have 36 inches for medium voltage switch gears. And then your working distance can change with regards to this, depending, for example, if you're working on high voltage equipment, like linesmen, then your working distance can be the distance of your insulated rod, for example. So the second question I have, question from Kresta Zumel. if a protective equipment has a maintenance mode, do we calculate the incident energy using the maintenance mode settings? So in this case, what I've done in the past mostly was I calculated the incident energy with the maintenance mode off, created a label for this, and then calculated the incident energy with the maintenance mode on. And then this gives you two different labels for the same equipment, one with the maintenance switch off and one for it on. Any other questions?
Simon, I have one more. I'm just typing over to you right now.
Okay, great.
Well, let me just read it to you. This is from Prem Devkota. I still don't understand how the working distance is defined. Can you please make it clear?
We'll show you my slide on the working distance. Hold on. So here you see the working distance. Basically, the arc flash energy has to be given to a certain distance. The source itself is the IS energy location, and then the more you go out, it's like a sphere expanding. So the more you're working from far away, the lower the energy will be. So there are three typical working distances. So it depends on the equipment type. So what you need to do to find the working distance is identify the equipment type. What's the voltage? So if it's 600 volt and below, you need to say, is the equipment a MCC or a panel board? Then it's 18 inches. Or is it a switchgear? Then it's 24 inches. And then if it's a medium voltage switchgear, then it's 36 inches. So it depends on the voltage. It depends on the equipment type. And then what it represents really is the typical distance between the live bus bars and the chest of the worker. So the reason why, for example, it's different between an MCC and a switchgear is that the switchgear construction makes it so the bus bars are farther behind in the equipment. So they'll be further away from the worker. So that's why the working distance will be higher when you're working on a switchgear. So I hope this makes it clearer. So I have another question from Georges Chaquette. 240, 120 volt single phase, do you calculate line to neutral arc flash? So basically for single phase systems, the IEEE 1584 is the one that states the method, and the method that they recommend is you use the same equations than you would use for three-phase networks, but you use the line to ground fault current instead. So you can calculate it, but you need to plug it in the formulas. That the formulas only exist for three-phase. So when you calculate arc flash, the formulas in the IEEE 1584 are defined for three-phase networks. But the standard says if you're single phase, you can plug your line to ground currents in the equations, and you'll get a very conservative result. So George has a question. So is there a language requirement for the labels? English, Spanish, French. So there's well, the language requirement depends on the country. For example, if you're in Quebec and your labels are all French, you should use French labels. If you're in the rest of Canada, in Ontario, for example, you should use English labels. If it's government utility, then you have to ask them whether they want bilingual labels or they want only English or only French. It depends on their workers. Like, are their workers bilingual or do they speak English only? This has to be discussed with the client. There's no specific language requirement, but the labels, you need to make sure that people can read them. So I have another question. Is installing a genset on standby with lower kVA than the normal service running only critical loads? So I'm trying to figure out what this question means. The what I'm getting at is if you run your genset at standby versus normal service, the arc flash will be different in both cases because the power rating will be different. So in your arc flash study, you should do a case with standby rating, and you should also do a case with normal rating. Then you'll have two different energy, and you pick the worst case one for the label. Then another question from Jim. What about equipment fed by 125 kVA transformer arc flash calculations and less than 240 volt CSA Z462? So basically this limit was changed in the IEEE 1584 2018 version. So the 2002 version stated that arc flash assessment was not necessary under transformers below 125 kVA and under 240 volts. But now this was replaced by under 240 volts and under 2 kA of available short circuit current. So the IEEE 1584 standard states to cut off your arc flash study at 2 kA short circuit. But if you want to consider equipment lower than this, you can, but the standard does not require it.
I have another question. I'll just read to you. If it is arc-proof switchgear, do we still need the arc flash label? By Philip Wood.
Yes, you still do arc flash labels. I think I got some precision about the genset. So the person wrote, oh, I mean out of the IEEE short circuit range. So yes, IEEE 1584 standard has a defined short circuit range for its model to apply. So if your short circuit for your genset is lower than the minimum, you can use the method to calculate the arc flash energy.
Simon, that's all I'm seeing. So if we don't have any more, I wanted to thank you and thank you for presenting and thank everyone for attending. And within a week, we'll get this the recorded video for this up on our website, and everyone who registered will receive an email with the link to it. Thank you very much, Simon.
Perfect. Thank you, Ted, and thanks again to EasyPower for letting me host this webinar.
Thanks. Bye-bye.